Thank you very much. So just very briefly, what I do at Cognizant is essentially work with customers in order to improve existing models, to create the state-of-the-art models from scratch, so AI, designing AI, and also to augment decision-making. And you'll see bits and pieces of this in this presentation that I will be giving, but also I thought I'd also kind of take a quick peek at what I think is going to be the more immediate future in AI. So I think I'm preaching to the choir. I spoke to some of you earlier today that AI does have a broad impact. I think by now that's quite evident. When we look at some instances of AI, we see that today AI has enabled us to improve the state-of-the-art on speech recognition. We have improved the state-of-the-art on handwritten character recognition, on diagnostics, even in applications that maybe 10 years ago, 10, 15 years ago, we weren't even expecting AI to be able to do. For example, automatic labeling of images, being able to describe in correct natural language text what's happening in a picture. Even when it gets it wrong, it's pretty close. We now have been able to do machine translation better than grammar-based approaches. And all of these, including things such as object detection in images and in video, are enabled by a technology breakthrough that we've had in the past 7, 8 years called deep learning. So everything that I showed you up until now, the catalyst that has enabled us to improve on the state-of-the-art has been a form of neural networks that we call deep learning. But deep learning has its limitations. Let's start with the name deep learning. Deep does not refer to some form of deep thinking or deep knowledge of the world. Deep here really means the number of hidden layers in a neural network that we can afford. And because we now know how to do backpropagation on very large networks without them overfitting, we can actually create networks with a lot of hidden layers. And that's great. It's wonderful, but it's not deep thinking. And then there's the learning part. Is deep learning really learning? Well, in most cases, not. Because what's happening is we use a lot of typically labeled data. And in a batch model, we actually train these neural networks offline. And they do generalize quite well. There's some really good abstraction that's happening. But then that generalization is used out in the field without adaptation, typically. So we're really not usually improving the deep network after it's been trained on that data set. So while very, very impressive, it's still not quite where we would expect our artificial intelligence systems to be. Furthermore, we have a problem, which is that we don't have a one-size-fits-all deep learning system. So we can't just take deep learning off the shelf and train it against data and expect it to work really, really well in a brand new domain. And so what's happened is that it's kind of job security for people like myself. We go in and we actually devise a new architecture, hyperparameters, even loss functions, activation functions. We put all those together in order to be able to exceed the state-of-the-art in a certain domain. There's no one-size-fits-all. And there's a lot of work, a lot of PhD hours that goes into building these architectures. So what I would like to introduce to you is another discipline within AI that might actually come to help and be able to overcome some of these challenges. And I think what's missing here is what I would broadly categorize as creativity. When we talk about designing a deep network, which I have an image of it here, immediately we're thinking that's a creative process. It's a design process where we have to put together these various different elements in order to address a problem. When we talk about designing a website, We talk about creative designers. It's a creative process. And of course, the bullet train. The nose cone of that bullet train looks kind of weird. It's not the most aerodynamic. When they actually designed it to be the most aerodynamic, it made a loud boom sound every time it entered or exited a tunnel. And so they had to actually be creative to be able to achieve both aerodynamicity as well as make it more comfortable when it entered or exited tunnels. And that was creative. I mean, it looks creative. Okay, so what is creativity? When it comes to humans, typically the way we're creative is we take the state of the art or some solution to the problem and we tweak it. And if that tweak works, we keep the tweak. If it doesn't work, we toss it and we try a different tweak. And this is essentially what we know in machine learning as hill climbing. It's gradient descent or gradient ascent, depending on which way you look at it. Just think of this terrain as a place where we want a mountain climber to find the peak. And if the mountain climber takes a step around where they are and decides to go with the step that actually elevates them a little bit, and then continues doing that over and over again, the likelihood in this terrain for the mountain climber to actually find the peak is pretty high. Now, even if they're on one of those hills, if we random restart, we're going to get the peak eventually, which is all well and good, and it is the basis of most AI systems today in RL and deep learning. But when we are faced with a search space that looks like this, then we're in trouble. This is what we call a deceptive search space. There are many, many hills. And, or when the search space is far too large to be able to do this. It's what we call a needle in a haystack kind of a setup. Or if it's too high dimensional. So in these cases, doing a hill climb is not necessarily the easiest way. And that's where we have to revert to creativity, usually these days in human creativity, to actually overcome that. But enter evolutionary computation. The start of evolutionary computation was actually with Alan Turing. This guy is such a genius. He came up with neural networks and evolutionary computation and AI and modern computing. And I think he died when he was 38 or something. I don't know. But that's where it started. John Holland actually popularized a form of evolutionary computation called genetic algorithms in the 70s. And it's inspired, just like neural networks are inspired by an oversimplified model of how the brain works. This is inspired by how we believe survival of the fittest and biological evolution works. Why is it creative, though? The approach is simple. We create a population, not a single solution. Remember when we said humans' creativity was a single solution that we tweak? In this case, we create a population of solutions, each slightly different from the other. And we always maintain this population. We observe how they work, how well they do in solving the problem. And we take the ones that are doing better and mix them and match them in creating the next population. That's the essence of an evolutionary system. So it's population-based. And so if I map the deceptive search space that we just looked at into 2 dimensions, and each little dot there represent one of the solutions, now it's as if I've parachuted a bunch of mountaineers onto this terrain. And by virtue of taking the ones that are doing better and taking traits from them in order to build new mountaineers, so to speak, I'm essentially getting a sense of the terrain itself. So the population is giving me a sense of what the search space looks like. And because of that, these systems, these population-based systems, are much more efficient in traversing these search spaces and finding solutions. They might not guarantee finding the optimal solution, but they do find close to optimal solutions very, very quickly in tackling all 3 of the problems that we talked about. We talked about very large search spaces. We've used evolutionary computation to find the solution to 70 multiplexer system, we know the size of that search space is 2 to the 2 to the 70. This number is so large that if you print it out in digits, 8-bit digits, it takes light 98 years just to traverse the number itself. That's how large it is, and there's only one solution. So very large search space. In material science, people have shown that the use of evolutionary computation can actually solve problems of up to 1 billion dimensions. That's very, very large. And it allows us to use concepts such as novelty or concepts such as trying to solve for multiple objectives. What does novelty mean? Novelty means that if I've actually visited part of the search space, that part is not interesting to me anymore. And so because I have a population, I can force the population not just to look to optimize against objectives, but also to look to get maximal coverage over my search space. And so I can introduce these sorts of concepts to make the system more creative. So let's look at this approach in action when we put it together with neural networks, with deep learning. I'll take an example. This is for chest X-ray classification into 14 different diseases. We use this because it's a good benchmark, and it's image-based. OK, so the task is the input is the image of the chest X-ray, and the output is one of those 14 classes. And let's say that rather than using a typical deep network, we want to start from scratch, and we want the system to actually automatically design the deep network that's best suited for this problem. OK, so what the system is going to do is it's going to create a whole bunch of neural network architectures and hyperparameters, train them partially, doesn't have to train them fully, but train them partially on the data, and see which ones do better. The ones that do better, we will take those architectures, mix them, match them, take bits and pieces of them, and create new architectures as the new population, and go through this over and over again. So by virtue of doing this, we're having the system automatically design the deep network architecture for us. So let's look at what this looks like. Initially, this is the best of generation, early generations. And you can see the candidate is very linear. The connections are all the same. The layer types are pretty much the same. But then we gradually start getting new modules. So the trick that we're playing here behind the scenes is not just evolving the architecture itself. We're evolving blueprints and modules. Modules are reusable subnetwork architectures, and they're color-coded here. I'll talk about why modules are really important, but just suffice it to say that we have two populations that are evolving simultaneously. One population is the blueprints that tell us how to put modules together, and the second population is the modules themselves. And how do we rank order them? Well, the blueprint, if it does well, that's, in the problem, that's how we rank order it. And the module, if it is utilized, and the utility is what we call the fitness of that particular module. You can see through generations, again, we just started the system and we stood back, but it looks like the system is actually creating more and more complex architectures, connections. You get skip connections, different layer types, numerous modules. We're getting reusability going on and so forth in order to solve this problem. It's almost autonomously coming up and creating the design for the deep network that we're looking for. And the results are impressive. We beat Google AutoML, which at the time was only doing hyperparameter optimization. And we come close, I think, we barely beat the human design, beaten to death result, starting from scratch. You can imagine that if we had started from the human design version, we could have possibly even done better. OK, now the other aspect that I talked about was multi-objective. As we're running this we're training for loss. So we want to reduce the loss function, and we want it to generalize the best on our out of sample. Now, we can actually look at this system as it's training and plot it against two different objectives, even though we're only training against one objective, but we can also plot it for a second objective, which could be, for example, the size of the network. Why? Because we want the network to be run on a laptop versus, a gnarly GPU box. So it's important for us to actually map that. If we do that, we have two dimensions. This is what we call a Pareto front. And the green line here that you can see is when we plot this while we're only training against one objective. The blue line, though, is if we train against both objectives. In other words, as the population is going from generation to generation, we maintain individuals that are the best in some balance of the two objectives. Surprisingly, well, probably not surprisingly, the system actually works better. It's more creative. It works better on both of the objectives. And ultimately, you see the blue line kind of overshadowing the green line altogether. So I can show you what this looks like for the, I think this is still the chest X-ray optimization. So if you look at these points, the dot on the very right-hand side is the most accurate. The most accurate chest X-ray classification system that we could get. The one down here is the one that is the fastest, the smallest, right? So it's not very accurate. But if we take something that's on the elbow, let's say point number 28 or something up there, this guy is only 0.38% less accurate, but it's 1/12 the size of the network that was the most accurate. So it has a really interesting balance of accuracy and size, and we can take it, and possibly that makes the difference between having to run it in the cloud versus running it on a laptop. Okay, so just to briefly also touch upon why we use modules and blueprints. Here's an interesting example. We have, this is a data set called Omniglot. It's 50 different character sets that we want to train against simultaneously. None of the individual character sets have enough data. So if we were to actually train a deep learner against just one of the character sets, it would not do well. So what's really important for us is this transfer of abstractions and learning from one character set to the other. What we're trying to use is this commonalities in patterns that might exist, and we just intuitively think do exist across characters. So how do we do that? We train, as I mentioned, using modules and blueprints, and we co-evolve the two simultaneously. And lo and behold, we actually exceeded the state of the art by around 30%. By doing this, you can see that we automatically had the system design deep networks, 50 of them for all 50 character sets, while sharing the modules. The blueprints can be shared as well, and you can see in some cases the blueprints are the same. In some cases, the blueprints and the modules are exactly the same. So that shows that that character set is, those two character sets are quite close. In some cases, though, they're very, very different, sometimes very complex. But the sharing of the modules is still happening. And that's how, with a very limited data set, we've been able to actually train against related tasks. Okay, let's shift gears now and talk about what more can we do beyond just, being able to create these AI systems automatically. What is it really that people expect from AI? When we go out and talk to them, they give us tasks such as what I've listed here. When you look at these questions that people are asking us, they're saying, if I had some AI, if only I could get some of these questions answered. When we actually look at them, it seems like the question that they're asking is mainly around prediction, insights, knowledge. Give me more knowledge on the data that I've collected. And if I get that knowledge, then I, as in the human, knows what to do. I have rules. I know, if I had the knowledge, I would take these actions. This is understandable, partly because that's the state of the art in AI. The AI in deep learning knows how to abstract against a data set, so it gives you insights. That's just basically what it does. Also, it comes from the fact that as humans, we kind of overestimate how well we know what to do based on the data that insights that our machines give us. But there are many insights, and I'm not sure if just adding to the reports is helpful. And often it's just, not very helpful, and we might not know what we need to do. So I would say that insights alone are not enough. And here's a few reasons, a few examples. Let's say that your AI now tells you with very high accuracy that you're going to miss your revenue targets. What are you going to do? Right? You still have a number of questions that you need to answer. And it's not trivial. We don't quite know how to answer these questions. So it's not just the insight here alone that would help us. Let's say that your AI tells you that your costs are too high. What are you going to do about that? Should we reduce costs across the board? Should we renegotiate supplier prices? Or invest in efficiency, or a little bit of all, where, how? The how of the decision is not given to us. And so we have to kind of come up with it. The other piece of the puzzle is the actual objective. We're never making decisions only for one reason. In fact, our organizations are multi-objective beings. We want to maximize sales while minimizing cost. But we're not very good at that. So as humans, we're not very good at multi-objective decision-making. And so we set up our organizations in a manner where we have, for example, a sales team that wants to maximize sales and revenue, while you have a finance team that wants to minimize cost. And they're always butting their heads together. But the organization as a whole can't be doing one extreme in exchange for the other. And so decision-making is important for us. And surely today's state of the art in AI can help us with decision-making, right? Surely if we're beating the grandmaster in chess, or we're beating the world champion in Go, AI knows how to make decisions, right? Not so fast. Deep learning is rather impractical when it comes to reinforcement learning and decision making. In the case of Go and chess, we know exactly what the rules of the game are. It's not like self-driving cars. We know exactly what the rules are, and we build it into the system. Furthermore, when we actually use deep learning in reinforcement learning, we make it observe the universe of possibilities. And typically, they're good at game playing like Flappy Bird. But if in the middle of Flappy Bird, suddenly you get Super Mario showing up, then you have a problem. Because suddenly you have a major change in the game that you had not observed. And reinforcement learning, when it was defined initially, was not really about observing a priori the universe of possibilities before you can solve the problem. So we need a different approach. And when we look at our businesses, businesses are all about decision making. So we need a different approach to decision making. So let me give you a little hypothetical. You want to ask your boss for a raise. How do you do that? You don't just walk into your boss's office and try different ways to ask for a raise to see which one works. You probably have one or two shots at it, and then you're done for another 6 months, right? What you do, probably starting the night before, or if you're me, a week before, you start thinking about how your boss would react. How do you do that? You actually have a model for your boss in your head. You, in fact, have a model for yourself in your head as well. And you have them start, enacting these various different scenarios of asking for a raise over and over and over again in your head until you come up with what you think to be the best strategy. I'm going to do it after lunch because he's not cranky. And I'm going to walk in and I'm going to be very polite. And I'm going to wear my best suit. And I'm going to give him the results of my project first before I ask for it. And I bet you it's going to work. Now, either it works or it doesn't. If it works, great. If it doesn't, you have 1 point of, my boss, after lunch, he's not as happy as I would like, or whatever, right? And so you learn that, and 6 months later, you have a modified model of your boss in your head, and you can actually play and enact this again, and hopefully be successful next time around. The point is, you're not doing this in the real world. But how are you doing it? We can actually take this and automate it. So we can take all the bits and pieces of what I just described. We can take all the context, action, and observations that you've had before in interacting with the world and create a model based on that. That's data science. But it's not any old model. It's a model that takes any context and action and predicts an outcome. If I ask my boss this way, and the day is sunny, then the outcome is going to be, yes, or the outcome is going to be no. That's the predictor. So we're creating a predictor. That predictor is a surrogate of the real world in this particular decision making. Now, once we create this surrogate, we now need to come up with a decision strategy. And in order to come up with a decision strategy, I would say our good friend evolutionary computation can come in handy again. Because evolution can search the search space very, very quickly, and it can try out all sorts of different strategies for taking a context and giving us an outcome, an output, an action, while optimizing against multiple outcomes. Remember, most of our decision making is multi-objective. Okay, so that's the prescriptor piece. So you can now think of this as a predictor, as a model for predicting how the world is going to react, and the prescriptor as a model that takes as input the context and gives us an action in order to optimize against the outcomes. Now that prescriptor gives us a decision when the actual moment comes up, and we use it in the real world, and we observe the results. So we're being very sparse in actually trying things out in the real world. The other thing that we're missing here is not only do we need a prescription, we also need a certainty. We need our system to tell us, in this particular case, our system is more confident in the prescription than in some other case. So if I walk into my boss's office and he's just been shouting at somebody else, and I've never observed this before, I've never seen this temper, I don't have a very good predictor. I don't have a good surrogate in my head. And while my system in my head might say, go for it and ask, it better tell me that I'm not very certain in this prescription because this context is unfamiliar to me. So these two go hand in hand, and they're very, very important, especially if what we're doing is creating an AI system that's going to augment human decision making. So let's take a little detour and talk about trustworthiness just very briefly. If the data that we're collecting is pretty tight, the error is not that much, then for the most part, we're pretty certain in the outcomes. But on the right-hand side, you can see that while the predictor, the model, is giving us pretty deterministic outputs, but the error is all over the place. So our certainty should be lower. So one way of dealing with this is to actually build a second model. We call this a certainty model. And this certainty model essentially is built based on both input and output observations. So residuals on the input and on the output. Why on the input? Because it might be a context that we're not familiar with. It's a situation we haven't seen before. So we should be less certain. Why output? It might be that our model is suddenly telling us something that it's never told us before. And we should take that with a grain of salt as well. So both input and output are very important. When you actually build models like this, I'm sure many of you have actually used the softmax out of your deep networks before, and you know that it's not reliable at all. What I'm saying here is always use a second model. In this case, we're using a Gaussian program, and put that alongside your initial model, and that will give you a certainty estimation that we can use. And when we do that, the certainty, I'm going to skip through some of these because I think I'm going to run out of time. But the certainty estimation, by doing so, is much better. And we've ran it on a number of different cases, and almost in all cases, once you actually have a certainty model, you can adjust the prediction. And so your prediction itself gets better. And in almost all cases, that happens. Worst that can happen is that you're as good or as bad as your original model. And we've tried this, for example, on age estimation for celebrity faces, and it actually improves significantly. Okay, so let's talk briefly about why AI-enabled decision-making, just as a quick reminder. So first of all, we have a system now that is adaptive. Why? Because we keep bringing in the latest observations, we improve on our predictor, and by virtue of that, our prescriptor gets better, and then we go back in. So we can keep up with the changing world, especially if the cadence of the decision-making allows us to do so, and usually in business decision-making, that is the case. The second is it's really not about big data, it's about good data. And in this case, we're hitting the good data because we're allowing the AI to do the data collection for us. We're being very sparse in actually going out to the real world. And we're only doing so when the AI thinks it's a good idea to do so. And so that's the points that we're actually collecting from the real world. We're being very conservative. And I talked about multiple objectives. It helps us because we're not very good at making decisions in the face of having to balance against multiple objectives. So where can this be used? I'll just give you a few examples. We can use it for price and incentive optimization. These are just some really real business examples of cases where you can use this, even within your own organization. We can use it in what is the most important decision-making that happens in insurance. It's when we want to do underwriting. And so on the left-hand side is all the information about a property. On the right-hand side, the AI has already given us a prescription. Note that it's also giving us a confidence in the prescription. It's saying I'm 85% confident that if you take my prescription here, which is to insure at 80K to 90K, that you're going to, your customer is going to buy from you. That's one objective. And also your risk is going to be low. Now that risk is measured 3 months out or a year out. It's lagging, but that's still fine. Now, the user can always deviate, right? The user can always say, hey, I want to try out 50K. I don't want to go with 80K. That's fine, because we run that through our predictor, and we come back and say, with this confidence, we think the risk is going to be higher. Up to you. We talked about designing web pages. We can now evolve web pages against live users as they're actually using the website for conversion rate, for time spent, for dollars spent, different objectives. Here's market mix optimization. What marketing channel should I use? How much? How much money should I put in the different marketing channels? This one's interesting because this is about, in a way, how should we assign people to tasks. This is subrogation. So if you're in a car crash, God forbid, your insurance company is going to be fighting it out with their insurance company, and their goal is to reduce the cost, the amount that they have to pay ultimately, right? So when we actually talked to the insurance companies, they told us the most critical decision that they make is the assignment of the human investigator, right? So we're like, okay, we can do that, right? So here, we're actually, the AI is saying, use this person for investigation, and we're 89% confidence that if you do so, you're going to recover 68 to 80% of the claim dollars, and the recovery time is 0 to 5 months. And you can always change that. You can click on a different one and get a sense of what would happen if you assign someone else. Fleet management, I'm going to go through the rest of these quickly. Fraud prevention. Notice we're saying fraud prevention versus fraud alerting on the fraud, because we're making a decision here and we can preemptively take tasks. How about HR? Right? There's a lot of decision making that happens in HR, from hiring to onboarding, performance. So maybe AI can help us with HR. I can see some people are feeling a little uncomfortable with AI coming in and helping with hiring, but we will talk about this in a moment. How about collections, to get it even more uncomfortable, right? You haven't paid your bill, and now an AI is going to help recover. What is the best way to do that? Or what is the best way to prevent you from being delinquent on paying a bill? It is used in trading. This is an example of a real trade that our AI system did. And on the face of it, it looks like 2 or 3 decisions. And it is, in fact, many, many decisions that the system has made. Initially, not to do anything, then at an opportune time to actually enter the market, then to sit on the position, and then at an opportune time to exit, and then not to enter again and make a healthy profit. Now, it doesn't always look this good, but if in most cases it does, then we're in business. Notice that unlike how trading was done using AI in the past, where it was all about generating a signal and then the trader knows what to do, in this case, we're saying no. It's actually the AI that not only observes the context, but is also taking the actions and then observing the result of that action. And I'll show you, in fact, this system is interesting because the representation was not deep learning. So rather than evolving a deep learner to do the trading, what we evolved was a rule set, a human-readable, understandable rule set. So I'll show you the rule set that was used for this trade. It. Copy it and make a lot of money. OK, so this rule set was actually evolved. So nobody actually wrote, oh, she's taking a picture. Nobody actually wrote the rule set, right? It was evolved from scratch. What we gave it was, here's the contextual elements, and here are the actions that you can take. I'll actually blow open a couple of these rules that were used in the trade that you saw. And just to read you what is happening here. What's interesting is that buy rule on the right-hand side, the trader is actually looking at its own position loss. How much am I losing, right? Before it makes a decision. So it's actually looking at its own state before it's making a decision. Then it's looking at volume over the last 30 minutes. It's looking at price normalized by volatility compared to 2 minutes ago. Decile trend, slow volume, blah, blah, blah. And then also note the action side. It says buy, yes, but it's not just a buy. It's saying buy at a limit order, not a market order. Don't put a TWAP or a VWAP. Use a limit order. And use the limit order at a delta of negative 0.6 of the last close price. That limit order may or may not close. You put a limit order out there. If it hits, then it hits. If it doesn't, it doesn't. So that's very interesting that the system came up with a way to actually test the waters and close the deal, a trade. And of course, similarly on the exit. OK, so it seems like there's a lot of places where we could use this AI now. We've broken out of this whole limitation of only using it for insights. We can actually use it for decision making. So what does this path to ubiquity look like? Our best guess would be based on what happened recently with computing and the web. They're both quite ubiquitous now, right? So where are we when it comes to, with AI, when it comes to the path to ubiquity? I would say that we have a number of milestones to pass. We're still at a point where the potential's there, but we're not there at all. To start with, what was really important in computing was open architectures and compatibility. That was what made the PC revolution actually take off. The equivalent to that to the web, I would say, was the HTML, the markup language that was standardized. So you could actually have browsers show your content everywhere. So, okay, those two steps, realistically, we're not quite there with AI just yet. Then came interoperability. So I'm sorry, this is all interoperability. So AI needs to get to a point where we have standards of interoperability. And we don't quite have that right now. It's kind of de facto. If your model is in Kuros format, you can load it by others and so forth, but it's not quite what we expect. Okay, then there was the advent of GUIs. What did the GUIs do? The GUIs allowed us to all become computer experts because it was very natural to navigate this system. Your grandma knows how to operate the operating system now as well. So that was a very important step. In the web, I would say style sheets were a huge step because you didn't have to worry about the look and feel. You now have to worry more just about the content itself. And so we do need interfaces for non-programmers. We need to get to a point where all of us are AI programmers. We can all set up AI systems. What was the next step? The next step, I would say, was the advent of Samsung's smartphones and iPhone. So why? Because now we all have a very powerful computing device in our pockets. So that was a huge step in ubiquity of computing. In the case of the web, I would say social networks. Because now we're all generating content without even thinking about it. We're actually creating web pages, literally. That's what we're doing. And we're adding content onto the web. So we need some form of system that allows consumers to train and deploy their AI systems. Not just be able to use them, but actually to be able to train and deploy them. And finally, we have the advent of cloud computing and the advent of the digital economy. We're not quite there with this one yet, but we're getting there. So that, I think, is the last step where AI would create an intelligence-based economy. And I think, I'll leave it up to your imagination as to what that might look like. But suffice it to say, we're still very far from this point. Which brings us to my last question. What will our role be in all of this? This comes up again a lot. When I was a kid and I thought about the future, I thought I'd be relaxing on a couch and everything would just be happening around me, just automatically, right? I didn't have to do anything, right? But it turns out that our role is much bigger than that. What AI gives us is, rather than having to engineer solutions, we have to articulate the problem. And in articulating the problem, the most critical piece of that is articulating the outcomes. What is it? Where is it that we want to go? What is it, the outcome that is the most interesting to us? I just showed you some application areas that, if you think about it, are pretty cringeworthy. If we allow AI to start doing our hiring automatically, or to pursue us if we're delinquent on paying our bills, we better set it up properly, right? And that's a big responsibility. So unlike what I thought when I was a kid, it seems like this shirking of the responsibility, just leaving it be and letting it just happen, maybe we can't do that anymore. So our role is, in fact, not to leave it to happenstance. And I would say that I'm not very comfortable leaving it up to this guy either. Nor to this guy. So here, but you know what? I'm gonna give you a few pointers that I think is important to think about. I do think that we're not spending enough money and investments into humanities and human sciences and this ethics of science. And in fact, it turns out that the whole discipline of ethics isn't even set up properly, in my humble opinion, because I've talked to a few ethicists, and the moment you say science of ethics, they're like, don't put those two words together. Ethics has nothing to do with science. But as an engineer, I need a non-ambiguous declaration of the ethics of my system. You can't just give me something that's ambiguous. I know why you do that. I know why we say hiring shall not be biased, because it's easier. If we say it's not biased, it's future-proof. If we don't define it properly, in the future, if somebody accuses us of not being biased, we can find the person that didn't do the biased hiring, and we can penalize them. But in the future, we have AI doing that, and we can't just, I mean, it's not satisfying just to penalize the AI. And therefore, we do need to think about how we articulate the goal. So let's think about the objectives. Let's codify the standards of ethics in a non-ambiguous way. Let's decide who is responsible. Today, and I think even the next couple of generations are going to have a hard time thinking that the AI itself is responsible. That might change over time, but currently that's not the case. We're not willing to reward or penalize AI or our machinery. And therefore, we have to decide whether, for example, the person, hopefully not, but hopefully the person that comes up with the AI is responsible. Hopefully not. I mean, that doesn't make sense at all to me. Or is it the person that's actually utilizing it? Or is it, so who's responsible? And then we need to lay the groundworks of defining where we're comfortable going collectively. And this is not a very small question. The last couple of attempts we had at trying to answer this resulted in Nazism and communism, and we really don't want to go there. But it's a question we can't avoid, I think. Maybe we can avoid it still for a few more years, but we have to get to it. And finally, I think we need to, practically speaking, try these systems out in sandboxes where we actually see the results, gradually roll them out. We have opt-in participants, including the regulator, including the ethics scientists, and as we observe, we refine, and we get it to a point where it makes sense then to publicly use them. Thank you.